Hello everyone. In this section, we are going to study the gravitational instability. Before explaining the gravitational instabilities, at first we will find the growth of a solid particle while it falls toward a mid-plane of a disk. So we consider the red particle is falling toward the mid-planes from the g equals g sub 0. G sub 0 is the initial height of the solid particles. A large particle falls toward the mid-plane of a disk faster than the small particles. A large particle always catches up small particles and captures them, increasing its mass. If you consider the large particle for the distance of the delta z, areas of these cylinders with the pi r sub p squares. R sub p is the radius of the solid particles. The mass inside of these cylinders contribute to the growth of large particles. Increase of its mass of the delta m can be calculated. Pi r sub p square is the areas. Pi r sub p square times delta z is volume of these cylinders. And if you multiply the density of the solid particles in a disk, we can find the increase of the mass by solid particles while it falls toward the mid-planes. We need to multiply the sticking probabilities. Z is the height from the mid-planes. So minus delta z becomes a positive quantity. So delta z is a negative quantity. So increase of the mass can be expressed minus r sub p square times rho sub dust times delta z times the p sub s. The mass of the solid particles can be calculated. 4 pi over 3 r sub p cube is the volume of spheres. Then times the density of the rho sub p, material densities. So from this equation, you can find the derivative of the delta m can be calculated 4 pi r sub p square rho sub p times the delta r sub p. So we could use these two equations, delta m, and then these two quantities is equal. Then pi is going to be cancelled out. R sub p square is cancelled out. You could find 4 rho sub p delta r sub p equal negative rho sub dust p sub s delta z. So from this equation, dr sub p dg can be calculated minus rho sub dust over 4 rho sub p times sticking probability of the p sub s. Then you can integrate in the both sides of the equations. drp, r sub p is changing r sub 0 to the r sub p. Integrals minus rho sub dust over 4 rho sub p p sub s dg. So the particle is initially located at the very highest position in a disk. So this is g sub 0 and falling. And then at this position, this is z. So starting positions at the g equals 0, the size of the particle is r sub 0. So this corresponds to g sub 0 and then z. Left hand side is easily calculated, r sub p minus r sub 0. And the right hand side can be calculated minus rho sub dust over 4 rho sub p p sub s z minus g sub 0. So r sub p can be calculated r sub 0 plus rho sub dust over 4 rho sub p times g sub 0 p sub s 1 minus g over g sub 0. We'd like to find out the size of the particle in the mid-planes. Rho sub dust times 2 g sub 0 is equal to the sigma dust, surface density of the dust particles, and g equal to 0. Then it becomes r sub 0 plus sigma sub dust over 8 rho sub p, p sub s. We could consider that r sub p is a 1 micrometers. So compared with the 1 micrometers, this part is much larger. So you can estimate using the Hayashi models. 7 gram square meters over 8. Material density is 3 gram per cubic centimeters. So it becomes 0.29 centimeters. So about 0.3 centimeter particle is forming when the small dust particle with a 1 micrometer fall to the midpoints. It grows to the 0.3 centimeter radius particles. So we summarize what we discovered. Small particles, sometimes we call the dust, are distributed in a disk. The typical size of the small size particle is 1 micrometer radius. So these particles fall to the midplanes. While it falls to the midplanes, it captures number of the small particles and increase its mass. Then finally, when it reaches to the midplanes, we expect the size of the 0.3 centimeter particles. So we expect the dust-rich layer might be formed at the midplanes. So this is a formation of the dust layers. So this is the end of the first session of the gravitational instabilities.